Okay, welcome to the 21st class meeting of the spectrally correlated random processes. We've just taken take-home exam 3, and as you have seen, the problem has some very interesting and important results. So let me review some of the results only, not the details. So this is the exam problem set. And even though there are 5 problems, many problems are very similar and incrementally changes the difficulty. And probably you've seen what is persisting and what is changed. So let me emphasize by reviewing that. So the theme is that we as an electrical engineer, especially with radio wave applications to radar and communications, we usually have real valued bandpass signal y over t that is the upconverted version of a complex valued random process. So we take the real part of x of t times e to the j 2 pi f sub c of t. And we are interested in the cases where this x of t is a complex random process having spectral correlation. And I found that we too much emphasize the second order cyclostationary random processes. So it seems that you may have some misunderstanding why this real valued bandpass signal exhibits some strong spectral correlation at frequency 2 times the center frequency. So I've decided to simplify the random process x of t as a real valued baseband random process that is also assumed y-sense stationary. And then I've extended it to a complex valued second order stationary process. So the theme is just x of t is second order stationary complex valued random process. And the question is, what is the property of real valued bandpass random process? Got it? And as you've seen here, the answer is very interesting. Y of t is second order cyclostationary with y-sense cyclostationary because it's real, so y-sense cyclostationary with fundamental cycle frequency, cycle period 1 over fc or 1 over 2 fc, depending on whether this x of t has non-zero mean or not. Okay, so in this case we have non-zero mean, and in this case we have zero mean. That is the kind of summary of the lessons I hope you obtain by solving the problems. Got it? So in the first problem, we simply assumed x hat as a real valued zero mean y-sense stationary. So it's a simplest case, such as BPSK digital modulation with excess bandwidth less than or equal to 0. So we do not have any spectral correlation at all, except that since it is real valued, we have conjugate symmetrical spectral correlation. And as you see here, we have fundamental cycle period 1 over 2 fc. Why do we have that? It is because if we calculate the autocorrelation function of the upconverted real random process, we have what? We have e to the real part of e to the j 2 pi fc t plus s factor somewhere. And this is the reason why we have this cycle period 1 over 2 FC. So you will see that you have seen that if you replace T with 1 over 2 FC and S with S plus 1 over 2 FC, then here this T plus S becomes T plus S plus 1 over FC, and 1 over FC cancels with this FC so that you have equality. Got it? So in problem A, when we had the real valued zero mean y sense stationary process, then the upconverted signal is y sense cyclostationary, of course, mean zero process with cycle period 1 over 2 FC. Got it? And in problem 2, we little bit modify the first problem. No, not yet. So in problem 2, we derive the bifrequency spectrum. Not this one, just a second. Just a second. Yeah. We derive the bifrequency spectrum of the real valued bandpass random process we used in problem A, and have seen this two variable function really has non-zero values concentrated concentrated on these three lines. The first one is F1 equals F2, and second one is that F2 equals F1 minus 2FC. And this is F2 equals F1 plus 2FC. And also, you can see, is it? Yeah. And also, you can see that here, the height of the impulse fence is related to the power spectral density of the real baseband process. And also, you can see that since this is real symmetrical in this problem, you see that the where? Yeah, probably something like that. So you have the same if I remember correctly. So which one? Okay, let's see. One. Just a second. Oh. Yeah, I'm not sure which side has positive one. Anybody? Probably this one. Yeah. Anyway, you check it. Okay. So the bifrequency spectrum really exhibits spectral correlation in our just a second, something's not correct. Okay. Just a second. Yeah, you are right. You're right. I'm sorry about this. Yeah, there is nothing like this. Okay. Actually, yeah, you have, yeah, you have something like this. Sorry about that. Got it? So So this height, so this is FC and that is 2FC. So your impulse fancies are 2FC apart to the nearest impulse fancies. So you have some shape like that. Got it? And we here changes the problem to still real, but non-zero mean case. And even though you could start from problem 3 directly, I wanted to give you some lesson by kind of detouring by solving problem 1 and then 3, because as you've seen, the Y now has almost the same bifrequency spectrum, but here you have Dirac deltas that reflects the non-zero mean of the random process y of t. Got it? So that is your bifrequency spectrum. Got it? So interesting thing is that this non-zero mean of x of t, the baseband signal, still only leaves the spectral correlation on the lines parallel to f1 equals f2 with 2 times f sub c apart. Interestingly, as you've seen in problem 3, due to the non-zero mean part, your autocorrelation function that does not exhibit the periodicity with 1 over 2fc. You need, here it is. Yeah, you need 1 over fc. Why is it so? So mu sub y of t is periodic with period 1 over fc. And your autocovariance function or autocorrelation function itself. Okay, autocovariance. Let me just say autocovariance. As we've seen, the periodicity with period 1 over 2 fc for the variable t minus s. However, for the cyclostationarity, Y-sense cyclostationarity with period 1 over 2 fc, this must be periodic with 1 over 2 fc. So the problem is that if this is period, then its integer multiple is also period. So the least common multiple could be is 1 over fc. That's why we have fundamental cycle period 1 over fc. Got it? And here comes the final result. And here, just a second. Yeah. So y of t is Y-sense cyclostationary with fundamental cycle period 1 over fc, even though, just a second, I forgot to turn it off. Even though your bifrequency spectrum always have non-zero values 1 over 2 fc apart. So be careful. The fact that bifrequency spectrum has impulse fancies that are separated integer multiples of 2 times Fc means what? It may have cycle frequency, this value, but the inverse of it may not be the fundamental cycle period, because you can also view this as what? There are 5 impulse fancies on which non-zero values could exist. You can interpret this one, right? What is important is that non-zero values spectral correlation can be there. I am not saying that only on these, right? So that's the reason why we ask such a question like problem 4D, right? Anyway, what about the cases, special cases where mu equals 0? In that case, since mean is 0, we have fundamental cycle period 1/2 Fc. And also, if we have a proper case, then what happens? If x of t as a complex second order stationary process that has that is proper. In that case, as you've seen and as you've derived, what does not exist? These things does not exist, and you only have these components. And if you have non-zero mean, then you have impulse on the center of this spectrum. Got it? So if I remember correctly, that is what we have. Just a second. Yeah, I believe so. So be careful. Be careful. The papers I have written related to the second order cyclostationarity, and that includes second order stationarity, I assumed zero mean cases, because non-zero mean case is very, how to say that, rarely occur in modern digital communications, because that wastes a lot of power in transmitting a tone signal. And that is kind of a non-written rule in modern communications. So that was assumed. However, our old analog communication signals, such as double sideband with transmitted carrier, in that case, we have exactly the cases like problem 3. X of t is real and it has non-zero mean. So you must be careful. Another thing why I emphasized this fact is that interestingly, some of the end-to-end neural transmitter and receiver pair optimized by modern machine learning and artificial intelligence technology, they intentionally, some of the results intentionally put a non-zero mean component in order for the receiver to resolve the channel uncertainty without other measure of channel estimation. So they use, for example, some constellation that has non-zero mean. For example, instead of transmitting QPSK modulation symbol, they slightly move this thing, then what happens? Suppose this is a single carrier system. Then your signal, complex baseband signal, has non-zero mean. And actually, that helps in the Shannon communication theory sense, allowing joint channel estimation and symbol detection. Previously, people had difficulty in calculating the capacity of a communication system when we have to estimate the channel. It's like they just said that, hey, in classical Shannon theory, we transmit a lot of data symbols for a long time because the Shannon theory is based on the asymptotic property of these transmitted symbols. So they assume that, okay, somehow we can estimate the channel. But that is true when we consider real baseband 1. And that is true when still we have a measure to resolve positive and negative direction. So people asked themselves the questions like, okay, then what is the true capacity of, for example, adaptive white Gaussian noise channel when we allocate some bandwidth so that the transmitter and receiver jointly and optimally estimate the unknown channel, something like that. And neural transmitter and receiver pairs, interestingly, adopted this non-zero mean transmission. In that case, even if we transmit complex baseband signal upconverted to the real passband, we may, in the long run, we may resolve this 180-degree phase uncertainty. At the same time, due to this large number of observations, we may estimate the channel properly as far as channel does not change. Got it? If channel is time varying, then it is another problem. But anyway, so be careful. Even though our digitally modulated signal so far are generally zero mean complex baseband signals employed. However, some man-made signals have non-zero mean when reviewed in the complex baseband. So be careful. Anyway, so I believe you enjoyed the problems. And the last one is related to the trouble with the properizing fresh vectorizer. Probably you remember that it has some strangely looking filter that is called capital G of F, and it's like kind of half Nyquist band passing a low pass filter. The problem is that suppose X of t is to be processed, a complex second or cyclostationary random process to be processed, then what is the problem? The problem is that since it has non-zero mean, then, and also cyclostationary, we have what? We have Dirac deltas that are 1 over t apart. So you cannot define the passband of capital G of F due to the presence of Dirac delta at exactly the origin. So we pass just half of the delta function, or we need to assume delta function is an approximation of positive rectangular pulse. That's very troublesome. For the fresh vectorizer, it's not a big problem because we may just adopt the passband that is exactly the Nyquist zone. In that case, even though we have non-zero mean, we have direct delta functions exactly inside the passband of filter. Of course, in proper case, you can choose any passband, the passband of the bandpass filter, as long as it has the total length 1 over t. However, in non-zero mean case, be careful about not to choose the starting point or end point of your passband as the integer multiple of 1 over t. Got it? So you need to be little bit careful in handling the second order cyclostation random processes using fresh vectorizer or properizing fresh vectorizer and also fresh properizer. Got it? So they are best used for the zero mean case. Okay. So I believe I've done with the exam problems. So let's go back to our discussion on the not this one. Yeah. Let me just stop. Yeah. Just yeah. Let's go back to our discussion to the shift invariant space subspaces and generalized Nyquist criterion. So let me ask you a question. What is your Nyquist criterion? So Nyquist criteria. There are many Nyquist criteria. If you ask LLMs, their best answer is what? Related with communications theory, COM theory, Nyquist sampling theory, and the Nyquist zero aliasing condition, something like that. And related to the control theory, they are talking about some stability issue. However, as we know that in communications theory, there are two things, not only the sampling related one, but also the intersymbol interference related one. So just consider a signal, digitally modulated signal that looks like this. Here, you may be a little bit bothered about the fact that I've chosen n from negative infinity to positive infinity. If you don't want it, then you may use shift invariant subspaces where generator is P of t and the period is capital T. In that case, you may consider a deterministic signal. And let me just use dn, not infinity. Or, okay, let me just use d hat, where that is finite. Got it? So this is the case where you assume digitally modulated signal. And this is the case where you just want to use shift invariant subspaces. Of course, this includes the cases where you have finite number of digital data symbols. Got it? Be careful. In the above case, we usually assume, not always, dn is a random variable and its realized version is some modulation modulation constellation. So d of n could be plus minus 1 in BPSK case and e to the j pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4 in QPS case, blah, blah, blah. Got it? If you just take a look at the Nyquist criterion for zero ISI in digital communications, they usually take the first point of view. And what is the definition? So definition is like this. Let's consider matched filtering. Okay, even though we may not need matched filtering, but the most common form has matched filter receiver. So it's like we have just x of t, and here p of t conjugate, assuming p of t is a complex valued finite energy signal. And here we sample at every mt. Of course, you may introduce some offset. In that case, it turns out that you need to shift this impulse response of the receive filter accordingly. And here we have the output. So x, y, and this is y of mt. And what do we want? In this case, what we want is that we want y of mt exactly equal to d sub m for all m. This is the time domain criterion proposed by Nyquist. So Nyquist, not as an information theoretic communication engineer, his era was not the era of information theory. So he approached the kind of classical communication theoretic sense. In that case, you don't talk about capacity, you don't talk about entropy, but usually you talk about, hey, what is the output of this receiver? And what could be a good criterion for designing the pulse, P of t. Right? So the question is, what condition does P of t satisfy for this one? So Nyquist adopted a criterion for goodness of a pulse. Okay, so what is a good transmit and receive pulse when it is used as a matched filter? Got it? And you may say that, hey, what if we have frequency selective channel? In that case, definitely matched filter itself is not a good choice in the receiver, right? So people actually generalized this result, and we can easily generalize the result in that case. But anyway, let's start from the simplest one. Ready? So there is no noise, since we also consider the shift invariant subspaces with generator P of t. So this is the criterion Nyquist had chosen. And why do we have this one? In general, y of mt can be written as something strange, like d sub m and P of t energy plus n not equal to m d sub n, if I remember correctly, and P hat of t minus m minus n t, if I remember correctly, where P hat of t is the convolution of the transmit and the receive filter, which happens to be, in this case, has the impulse response that is the time reversed complex conjugate of it. Got it? So actually, this one is, okay, this one is nothing but p hat of, sorry about that, yeah, p hat of 0, as you see. When m equals n, you have d sub m, p hat of 0, capital T. So this is the one, 0, capital T. Got it? So Nyquist just regarded this as interference. And this interference is what? Yeah, these interferences are from what? Other symbols, not d sub n. So there are many, many symbols, and this is regarded as an inter-symbol interference or due to the unwanted symbols. And in this model, since there are countably infinite symbols, we have some kind of symmetry. So if we change m with m plus 1 or m minus 1 or m plus million, still we have almost the same case. We have intersymbol interference due to these terms. Got it? So what is our answer? The answer is the derivation is abundant actually, and the idea is just simple. You can show that this is nothing but the condition that p hat of nt equals delta sub n. What does that mean? If n equals 0, it is 1. If n is not 0, it is 0. So simply, Nyquist criterion in the time domain is the Nyquist criterion in the time domain on its time autocorrelation function of P of t. Got it? Then how can you derive the equivalent frequency domain criterion? How can you do that? And it's not that difficult because we know what happens when we sample a continuous time signal uniformly with equal spacing capital T. So let me little bit deviate here. Suppose you have some pulse g of t, that is a continuous time signal. And suppose you sample this one at every capital T to generate a discrete time signal g. Let me just abuse the notation. But then this one has what? Discrete time Fourier transform. Capital G of e to the j2 pi f. And the question is, what is the relation between this continuous time Fourier transform and that discrete time Fourier transform? So it seems that it's so confusing. So let me use just H. Got it? And you can easily show that such an amazing result. So as we all know, the DTFT over discrete time signal must be periodic with period 1. However, here we intentionally put capital T in order to have a better link between the continuous time Fourier transform. So the left-hand side has what? Period now 1 over capital T. So this is period, has period 1 over T. And the period is due to the periodic extension of the continuous time Fourier transform by shifting the continuous time Fourier transform by integer multiple of 1 over T. And here comes the scaling coefficient that is related to the sampling rate. So we have sampling rate, and we have so-called folded spectrum. Now, let's use these results from signal gen systems to our conversion from time domain criterion to frequency domain criterion. Or if you want, time domain 0 ISI condition to its equivalent frequency domain 0 ISI condition. Since P hat of T is simply convolution of T and T of negative T conjugate, we have what? We have what? This one is due to the convolution property, we have convolution of P of T, Fourier transform of P of T and Fourier transform of P conjugate of negative T, which is P conjugate of F. So we have magnitude square of P of F squared, magnitude square of P of F. Now, this continuous time signal P hat of T is uniformly sampled, right? So what is the discrete time Fourier transform of the left-hand side? Discrete time Fourier transform is simply after we replace F with Ft. Now, what is this one? This discrete time signal has what? It has constant, right? So this is 1 for all F, I believe. Got it? So if you really want like h of e to the j 2 pi f, then you need to change this one, which is not that important, but like this one. Just a second. It's not that important, but anyway. Yeah, f minus 1. I will not write it anyway. So this is the result. Am I right? Just a second. Yeah, I believe so. Yeah. So this is the result. And now we may little bit generalize this one. To have the receiver structure like this. And we still want no intersymbol interference. Actually, you can modify P hat as what? P of T convolved with Q conjugate of negative T. Then you eventually have sorry, L. Such a result without much difficulty. This can be said a kind of orthogonality between P of t and P of t minus nt conjugate. And this could be interpreted as the orthogonality by orthogonality between P of t and Q conjugate of t minus nt. Why is it so? Because if you convert this one and that one in the integral form, what you will have is this one, and here that one. Got it? So this time domain criterion can be written in this form. So P of t has orthogonality to its time-shifted versions by integer multiples of capital T, and P of t has orthogonality with Q conjugate of t after shifting by integer multiple of capital T. Got it? So sometimes this is called orthogonality criterion for Nyquist condition, and that is called bi-orthogonal. This one is called the bi-orthogonality conditions for Nyquist zero ISI criteria. Got it? And you may wonder why I suddenly talk about this very undergraduate-like result in this graduate level course. Because we can very simply write this result with folded spectrum using our vectorized Fourier transform of P of t. And the result is very interesting. So let the vectorized Fourier transform of continuous time signal P of t as P underscore of f. And you know what does this mean. You may just regard it as a fresh vectorizer output Fourier transformed. Got it? And here goes Q underscore of f. Then the orthogonality. That is time domain orthogonality, right? Now can be written as what? Like this. You can easily see that the inner product actually gives you folded spectrum. And you may say that, what about outside the Nyquist zone? Actually, this signal is periodic, so we just need to focus on Nyquist zone for f. Got And the bi-orthogonality is really bi-orthogonality in terms of two vectors, P and Q. or if you want, Q and P. It's not difficult to show this. So in a artistic sense, which one do you prefer? This folded spectrum notation to say that I have orthogonality in the frequency domain, or this trivial and clear orthogonality condition in terms of the vectorized Fourier transforms, right? These are really say what? P vector inner producted equals 1 and P vector inner producted with Q equals 1. And you may say that, hey, where is 0? Because orthogonal means something must be 0. And there comes another one. So here goes our multi-stream transmission case. So now suppose our x of t is summation of multiple digitally modulated signals. Suppose L equals 1. Then this summation goes away, and we have the original sigma d sub n p of t minus nt back, right? But now, how many digitally modulated signal do we have if we limit lowercase l into 1 to capital L? Then we have capital L signals, right? So capital L digitally modulated signals, or capital L streams, if we call each one as a stream. So this is a simple generalization of our previous signal model, right? And we can consider the deterministic case similarly. And here, finite. Got it? So each stream is constrained to be a finite energy signal, even though we may have countably infinitely many non-zero terms. Here, D and L could be some else constellation. And each constellation may be different. First one is BPSK, second one is QPSK, third one is 16 QAM, blah, blah, blah. Now, what is our orthogonality Nyquist criterion for these multiple streams? So here goes x of t. And we have here P1 conjugate, P2 conjugate, PL conjugate, and we sample at every MT. And we have Y sup 1 MT, Y sup 2 MT, dot, 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 Y sup L MT at the output, because we have L branches. each branch has matched filter matched to the else transmit waveform. And we want there is no inter-symbol and inter-stream interference. So you see why I love interstream. I love to call each component as stream. Still, it's interstream interference and intersymbol interference. Sometimes I named it ISISI, and suddenly ISIS became a kind of name of terrorist organization, so I dropped that one from my papers. Anyway, ISI. Now, you now find that this is nothing but the previous bi-orthogonality criteria. But with what? At the, for example, first sampled output, all the terms related to the other waveforms is 0. For example, the first one requires what? First one requires P1 hat of NT equals delta sub n, right? But second one requires what? P1 convert with P2 negative T conjugate sample that NT equals 0 for all n, something like that. 1T, yep, I believe so. P1T convert with PL conjugate of negative T sampled at NT is 0 for all n. And easily, you can show that the first one is simply what? Using L. Nice, okay. In this way, except the first one, all the others are exactly 0 for all f. And now, using the vectorized Fourier transforms, what do you have? So the inner product between the vectorized Fourier transforms gives us what? This is just normalization. Orthogonality, 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 orthogonality. And this holds for all what? You may consider the second branch, third branch, fifth branch, then what do you have? So the first one can be simply written as what? So here, E sub 1 is the standard basis with the first entry 1 and all the other entries 0. Now, you continue for the second branch, third branch, and fourth. What do you have? You change this one, and you change that one. And eventually, you have this interesting result. Just a second. Superscript. And we may just put these vectorized Fourier transforms all together and use capital P matrix. And we eventually have this result. Got it? So you have a matrix that has columns as the vectorized Fourier transforms of these pulses. And then Gramian, usually we call these inner product type, matrix inner product type thing as Gramian. This Gramian matrix is what? Scaled identity for all F in the Nyquist zone. Got it? So actually, even it looks like a single equality, you have countably infinite number of equalities because your F can take any real value inside in the Nyquist zone. Got it? So this is the orthogonality, and we can easily generalize this to bi-orthogonality, introducing the matched filters, matched filter the impulse responses Q sup 1, Q sup 2, blah, blah, blah. So we eventually have what? This one for the bi-orthogonality. Got it? During the derivation, you've seen that actually we didn't use the fact that d sub n, for example, in this model, must be from same modulation constellation. It doesn't matter, right? We just use the fact that actually more like this one. D sub n could have non-zero values for countably infinite places, but it doesn't matter, right? We just want the nth sample equals d sub m. It could be any number. So actually, this result, orthogonality and bi-orthogonality, in terms of the vectorized Fourier transforms, are better fit to the shift invariant subspaces theory. So it's like the subspace spanned by the columns of capital P matrix is what? Kind of orthogonal to the subspace spanned by the columns of Q, except the S column and the S column in P and S column in Q, but they show what? Non-orthogonality, right? Got it? Now, we have just covered this part, subspace, shift invariant subspaces and Nyquist criteria. The problem is that why this is related to the translation series representation of a cyclostationary random process. So our question is that why we consider as the next topic the translation series representation of cyclostationary random process. And probably you remember the point where I deviated to the Wigner distribution function and other things. And at that point, we were studying the mean square periodic random process, where we study the KL expansion of time-limited random process. And actually, you will find that this translation series representation is very closely related to the KL expansion. Since we don't have enough time, let me just remind you some important results related to the KL expansion. What was that? We had the random process for simplicity restricted to the interval 0 to capital T. T is not the period or cycle period, it's time limited random process. And we assume that what? We assume what? We assume the autocorrelation function, which is a two-variable function, is what? Is given as a kind of kernel to the Fred-Hoelom integral equation. So we want to find V sub I of T, the time-limited signals, that satisfies this integral equation called Fred-Hoelom integral equation. And suppose we have found countably, possibly, infinite number of such pairs, eigenvalue and eigenfunction pairs. Then what can we say? Here, we may assume X is real or X is complex, it doesn't matter. But usually X is assumed real, so let me just assume X is real. In that case, from the property, commutativity property of multiplication, you can show that it's symmetric in real case. And also, it is positive definite. Positive semi-definite for all finite energy signal W of T. Got it? So as we've done in the eigenvalue decomposition of a positive semi-definite symmetric matrix, we can find not only countably infinite pairs of lambdas and v's, we can find orthogonal waveforms. So there goes so-called Mercer's theorem, saying that due to this fact of the autocorrelation function, we have the autocorrelation function written as what? As a summation of lambda sub I, V sub IT times V sub IS. Then what do we have? By using these V signals, we may obtain something interesting like this. you may just drop this, sorry about that, square root of lambda sub I if you want x sub i's have unit variance. Yeah, just a second. Am I assuming zero mean case or not? I believe it doesn't matter anyway. Yeah, something like this. And here, xi is obtained by computing this projection or inner product. Am I correct? Yeah. So let's delete this one. Yeah, this could be easier. Got it? And, no. Let me keep lambda I. In this case, interestingly, this x vector has uncorrelated random variables. So xi and xj are uncorrelated. And you may have the covariance of xi equals lambda sub I. Got it? So this is the result. And what we are going to do is that we are going to extend this one to a vector version, actually. So just consider we not only have a time-limited single random process, but also have multiple random processes. Then what do we have? We may replace this r sub xx as r sub x underscore t comma s. And we may have what? Since this now becomes a matrix, you have what? You have vector valued signal as an eigenfunction, right? And that is exactly what we are going to do. And since it's time's almost over, let me give you a hint. So here is a cyclostationary random process. Somehow we find equivalent vector valued random process, which is stationary. So let's assume that we have stationarized this one. Then, since this is, let's say this is real and not real, not good. Let me just simply assume proper complex. Y sense cyclostationary with cycle period T. And here goes the fresh vectorizer. Then we have Y sense stationary proper complex random vector process, right? And now this one has what? This one is Y sense stationary process. We have autocorrelation matrix. And related to this one is power spectral density. So we apply the term by term. Let me just say this t minus tau if you want, or t plus tau comma t. Then we have matrix valued power spectral density of X, parameterized by just that. Got it? And what you do is that, since we use the property that this is Hermitian symmetrical matrix with positive semi-definiteness, we apply eigenvalue decomposition, especially orthonormal eigenvalue decomposition to this one. Then we may have something like this. Got it? And then we inverse Fourier transform to have the autocorrelation matrix that are related to the inverse vectorized Fourier transform of our eigenvector valued signals. And this gives us something like something like this. Got it? So we've seen this one in the Nyquist criterion for multi-stream case, right? And eventually you will see that from the autocorrelation function, we find the power spectral density matrix by applying orthonormal eigenvalue decomposition and inverse Fourier transforming it. We have what? We have something like this. And here, interestingly, they are uncorrelated sequences. Got it? So we have uncorrelated sequences for each stream. And if I remember correctly, we have Y sense stationary D of n, something like this. Got it? And we may have, I believe, uncorrelated symbols too. Okay. Anyway, that's all for today.